Okay, so we are continuing from the point that we have left a lecture ago. So what we have said last time, we have discussed random process descriptions. We had joint p.d.f description that we have given, and this is the easier description, which is called the moment description. We have first order moment descriptions. Again, this is the topic of last lecture. First order moment description is very simple. You have a random process and you evaluate this process at a specific time, let's say t1. This becomes a random variable. Then you evaluate the mean value of that random variable. Okay. So if you do it for all times, for all t1, you get a function, time function. This is called the mean function of this random process. Okay. So this is part of the last lecture. Again, we have second order moment descriptions. So for the second order moments, as you see, we have two random variables. So when we take the product of these two random variables and take the expected value, this becomes a second order description. So for two different time instants, we evaluate this random process and then take the expectation of the product. So this becomes the autocorrelation function. I will explain these autocorrelation functions later on in more detail, but this is the definition. So this should be, of course, given for all t1 and all t2. Similarly, we have covariance function. So covariance function and autocorrelation function is very similar. If you assume that this mean value is equal to 0, this is 0, this is 0, then you are not subtracting anything. Then you are just multiplying samples of the random process. So you may say that in this bracket, I have mean subtracted, mean value is subtracted from this. So I have a 0 mean random variable over here. I have a 0 mean random variable over here. So this is the product of 0 mean random variables. And if I do this product, it's all identical to the autocorrelation function. Only difference is mean is subtracted at the first step. Okay. Okay, so if you do this, you have four terms over here. x1, x1. Sorry, x at t1, x at t2, their product gives you this. Then this times that, this times that, and this times that. If you evaluate these four terms, then you get this. Okay. So both of these autocorrelation function and covariance function is important for us, but later on we will discuss their meaning. So right now we are trying to understand, how we derive these descriptions. Okay, again, last time we have covered this random slope signal. So let's remember what was that. So I have a straight line passing through the origin. Furthermore, the slope of this straight line is limited to 0, 1 interval. And I'm selecting this slope from the uniform distribution. Okay. So the question is, how can I describe this random process in terms of its moments? First order moment. We have done this again in the last lecture. So you evaluate this random variable or random process evaluated at a specific time, let's say t1. Then you evaluate the expected value, the mean value of this random variable. So this expectation is then over this density, okay, xt1 density. Last time we had derived this density. Maybe you can remember, this was like uniform distribution. It's not very complicated, but in 0 to t1. So what is the mean value of this? t1 over 2. Okay, it's not very complicated. So again, this was derivation of last time. But in general, we don't do this p.d.f derivations. We use the definition of this random process, that is xt1 is equal to a times t1. Now you see that the expectation is over here a. The equality of these two is interesting, and this is a fact of expectations. So you see that t1 is a deterministic quantity, it goes out. Expected value of a is 1/2, so you don't need to do anything. If you know the expected value of the a, this moment description is just simple evaluation of this. Okay? So this is the thing about moment descriptions. They are much easier to calculate. Okay? Now the second order description. This is new. We haven't done this in the last lecture. So what do we have? I'm trying to evaluate this. So this is a function of two variables, two evaluation times. So I should calculate this product. Random variable number 1, random variable number 2 multiplied, then expectation is over whatever random inside of this argument. So this time we need the joint p.d.f to evaluate this. Joint p.d.f of, let me write x1 and x2 is needed. Again, we have derived this. Maybe you can remember we have even sketched that one. Okay. But the thing is that if I include the definition of random process, so I have a times t1 times a times t2 for this one, where a is the only random quantity. So this expectation is over a. Okay. So this becomes expected value of a squared. So this is the random quantity, only random quantity, times t1 times t2. These are sampling times. I know those times. So this time it's not the expected value of a, but expected value of a squared. So let me go over here. Then this is equal to 0 to, well, 1 a squared fa of a squared fa of a dA. And this is just 1 in this interval because this is uniform distribution, times, this is this part, t1, t2, and this is a to the third power divided by 3. So I have t1, t2 divided by 3. Okay. So as you see, extremely easy in comparison to the p.d.f finding, isn't it? So this is the advantage of moment descriptions. So if I know this, can I calculate the covariance function? So Cx is the covariance function. Again, these are right now just some numbers or some functions. Mean function is easy to understand, I guess. It's the mean value as a function of time. So this is second order description. I will talk about these descriptions later on. Right now we are just calculating and comparing this calculation with the p.d.f calculation. Okay. So this is, let me use this result. Rx t1, t2 minus mean function, this. So this is then equal to this one minus mean function at t1, mean function at t2. So this is 4, this is 3. 4 minus 3 is 1. I get this. Okay, so this becomes the covariance function. So what else? For example, if I, well, calculate the variance of xt1. Variance is a second moment also, because the definition of this variance is am I right? So this is a random variable itself, minus its mean. You take its square. This is the definition of the variance. Okay. So does this thing look like this one? Or this definition? So this is covariance function of x evaluated at the same time instant, t1, t1. Okay. So this is the reason that this is called covariance. Okay. So this is the variance standard definition, but if I have two products, if I have two random variables, this is called pairwise in a way, covariance function. So if I do this, I get this result, I guess. Okay. So this is the variance. Well, this is the mean of the random variable evaluated at t1. Okay. That is it. Now, this is the end of this example. Now, what we would like to do is now have one more example on this. So random slope example was nice, but it was more like pedagogical example than somewhat like an practical or an engineering type of an example. This was like very nice for our purposes in terms of learning. Now this is our second example. This is again, it has a name because I will refer to it. This is called random phase cosine. Now my random processes defined like this. So as you can imagine, we face such signals all the time, especially in electrical engineering. So what kind of signal is this? This is what we call the AC signal. But we see that the amplitude is not random, frequency is not random. Only thing that is random is phase. Okay? So assume that you turn on your oscilloscope, and on the oscilloscope screen you see a cosine. But you cannot adjust its phase. Okay? In practice, in the circuit laboratory and so on, you cannot adjust the phase. So it has a starting phase, and you may assume that this is like uniformly distributed. Similarly, in many applications, you receive a signal and you have no idea about its phase. Okay? So you receive a signal from your antenna, and you know the frequency, perhaps, because this is your radio, but you have no information about the absolute phase. Maybe you can talk about phase differences at two different places of your circuit and so on, but not the phase, perhaps. So what is this example? It says, find joint p.d.f and moment descriptions. This is a little bit more practical, but again, this would be an easy example for us. Well, first of all, do we understand this problem? So let's sketch, I always do this, some realizations. As I have said, realization is a technical word. So what do I mean by this? Assume that you turn on your oscilloscope according to this model. Now, let me have A minus A, some lines, this. So I see as something like this. This goes on. This goes on. This is a function of time. Okay? So what's going on? What do I mean by this? There is a sample space. This is abstract sample space. Then from this sample space, you select a phase. Okay, this theta, you select a phase. So let me call this is 1. So let's say that this 1 is when theta is equal to, let's say, 45 degrees. Okay. So this becomes x, let's say this, and t. 44, theta is equal to 45 degrees. Now I may have different thetas. Okay? So this is just one of these realizations. What else can it be? Maybe it's something like this. This is the red realization. Okay. So let me correct this a little. Okay. So this red one is tau 2. So this is like theta is equal to, I don't know, 100 and so this is decreasing. So this is, I have this 0. Okay, let's say 10 degrees, something like that. Okay, this is this one. So what is common in between those two things? Well, the period, because this is deterministic, amplitude, it shouldn't change. So this is related with the period. Let me write period. Okay, so the period is supposed to be the same. Amplitude, the maximum value that it can take is A, minimum value that it can take is minus A. It is the same. So one more realization, just to be, sure on this. Okay, so this is tau 3. Let's say that this is theta is equal to 150 degrees. I'm just making these numbers up. Okay, that is it. So what's going on? So as you see, I have infinitely many possibilities over here from 0 to 360 degrees. So what's my goal? My goal is understanding this random process at different times. For example, if I evaluate this random process at time, let's say, t1, so this is t is equal to t1. So what do I observe? I observe that if it happens to be 45 degree, if I'm on the black curve somehow, black realization, I'll be observing this, or that, or this one. But as I have said, I have infinitely many over here, infinitely many. It's like uncountably infinite. Many possible realizations. It's just a sketch showing 3 of them. Okay. Now the issue is, what is the density? What is the density at T1? Okay. Now I will be doing the same thing. I will be having 2 observation points, T1 and T2 later on. Then I will be calculating maybe their autocorrelation, etc. 2 different times. Okay. But right now I have first order description. For the first order description, I'll be doing just this calculation. So this sketch is very important. If you don't understand this sketch, or if you don't, if you have, say, doubts about how we derive this sketch, then probably you don't, fully understand the definition of this random process. Okay. So that is obviously the most critical thing. Okay. So let me see. First order descriptions. Or let's say, let's focus on p.d.f. First order p.d.f. description. So what's my goal? Now I will be assuming that there is an x1 random variable defined according to this. Okay. So this is obviously this random process evaluated at t is equal to t1. Okay. So only thing random is again theta. So what is the density of x1? Obviously this is more complicated, but in any case this is a known density. This is the unknown random variable whose density is unknown. Again, this is one function of one random variable. I should be able to calculate this. So what was theta? Let me write this. Theta is uniform 0 to pi. Okay. Now, I would like to do the following. Omega, not omega t1. I have called this something alpha. So if I have this alpha random variable uniform in omega t1 plus 2 pi. So what kind of equality is this? Now this is the definition. x1 random variable is this definition. But how about this one? Now, what's going on? So it is actually equality in distribution. So when I write this in brackets d, so this is equality in distribution. What do I mean by that? Assume that you are writing a MATLAB function. You first generate theta like this and add a number, so it's a fixed number. Or you can generate a random number from this distribution. Do you think you will be getting the same result? Obviously you will be getting the same result because the argument of this cosine, this density, is identical to this density. Okay? This is uniformly distributed. Over here, if you add a constant number to this random variable, it's just shifted. Okay? This density is shifted towards here. Omega t1 plus omega. Something obvious, but we need this equality in distribution. Otherwise, it can be confusing because you don't see any alphas over here. What's going on? Okay. Now, how about this? One more equality. Let me write here phi. Another distribution. Random variable. How about this? If I write phi as uniform in 0 to pi. Do you think this makes sense to you? This is the critical step for this calculation, by the way. Okay. So how can this was easy. Passing from here to there was easy. How about from here to there? So this time we are thinking about the properties of this function. So cosine is a periodic function, isn't it? Cosine is a periodic function with period 2 pi. So that means that, if the argument of the cosine can be shifted by 2 pi's in any amount that I like. Okay? So I can subtract 2 pi's, 10 pi's, 20 pi's if I wish, or add. So that means that if this is a uniform distribution somewhere, starting from this part, this is omega t1, and this is 2 pi. So I can subtract this and it won't be affecting the evaluation of this cosine function. Okay. Now you can say that, okay, after this subtraction, some parts of this distribution will be, shifted towards the negative part. The other parts will be shifted towards the positive part. At the end, you get a flat distribution over here. This is constant, this is flat. So in the 0 to 2 pi interval, in a fixed interval, what do you think? It will be again after this 2 pi subtraction or addition. There will be also a flat distribution over there. Okay? This is the property of the cosine being periodic by 2 pi. So that is the idea. Now I'm evaluating this random variable from this, because I have the equality in distribution. Of course, if this is not a uniform distribution, if this is not flat, if I subtract it, in the 0 to 2 pi interval, what we call in signal processing, there can be some aliasing. Do you understand this kind of alias? Maybe you'll be seeing it in some other course, but if you subtract it by 2 pi's, for example, this is over here somewhere. Let's say this is at 5 pi, and something like this. And this is ending at 7 pi. So if I subtract 4 pi over here, then this will be over here, isn't it? Then this will be going like this, and it will be entering like that one more time. If I subtract 4 pi from this one. But since this is flat, it doesn't matter how I subtract this. At the end, I will be getting a flat line in the 0 to 2 pi interval. That is the main idea. Okay. Okay, let me erase this because it's too detailed. So once we understand that, now the problem is a little bit more simple, but something interesting. Let's make a note. So this distribution, this, let's say, random variable, has no dependence on evaluation time t1, because there is no t1 in the definition. So if you want to generate x1, you see that this x1 can be generated by picking a number from this interval and then taking its cosine and multiplying by a. Okay? So there is no t1 dependence. In the earlier one, random slope, there was an obvious t1 dependence. Okay, next task. So if x1 is something like this, uniform in 0 to pi. Now, how can I find the density of x1? Well, not phi, I have called this phi actually. So this is a random variable, it's a capital phi. Okay. I have this. So how can I find this distribution? This one's distribution. So the density of x1 is the problem of interest. How can I find this? Well, maybe you will remember this one. If I call this a function, g of phi, so what kind of function is that one? G of phi is, okay, phi, a times cosine, am I right? It's something like this. So this is a, this is minus a. So this is pi over 2, 3 pi over 2, 2 pi. That it repeats as we have said. But since, okay, so phi is mapped to g of phi, this function, according to this rule. Now I will write the following first, and then let's think about it. X of t1 x1 is equal to, x1 is equal to f of phi I have something like that. Do you recognize such a formula? You don't? Again, this is one function of one random variable mapping. One function of one random variable mapping. This should be in your lecture notes of earlier courses. Maybe it can be in the review part of Ahmet Hoca. I don't really know, but this should be somewhere, being discussed because this is something very important. So what's the meaning of this? So let me tell you the meaning, that maybe that will refresh your memory. Now, the issue is the following. Now, I want to find the density of this. I want to find the density function over here. So select an x1. Okay, let me select an x1. But my selected x1 is, just to make note, it's less than in magnitude a. Okay? So this is my x1. It is smaller than a, it's larger than minus a, somewhere in between, in the range of this cosine function. Now I will call this locations phi 1, 1, phi 1, 2. These are these two. Okay. Now let's assume the following. You are looking for the probability, let's say, of having random variable have the value of x1. This is not exactly correct, but for the sake of simplicity, let's do this. So how can I have the value of x1, whatever it is, let's say 1 over 2. That would be 60 degrees over here, isn't it? Because a over 2, that should be 60 degrees over here, isn't it? And this should be minus 60 degrees, because in other words, I can never have a over 2. So, but this is not the probability, this is the density function. So we do the following. We say that, okay, I am looking for a probability around a over 2. Okay? So we take a very small interval over here. Let's say delta x. Okay? Then we get other intervals over here. Do you remember this a little bit? So this is delta y of first one. This is the other intervals over there. Now, this is the probability calculation then. You are looking for x1 to be in this interval. Now this is exact. x1 to be in this blue, let's say boldly shaded interval. So how can it be? It can only be if your phi is in this interval or in this interval. Am I right? Because look at these mappings. These are the borders. Okay? That's the only possibility. So maybe this is again a over 2. So this is like 0.1 unit interval around a over 2. So the question is, how can I end up with 0.1 interval around a over 2 value? Okay? That is the issue. So clearly this phi 1, 1, phi 1, 2 is in this set because these are at the middle. So if you check this, now you do the following. If this is x1, this is delta x is equal to that. This is phi density at phi 1, 1 delta y plus this approximate phi density phi 1, 2 delta 2. So this is what I have said. If you have an outcome in this interval, it can either come from here or from there. Okay? So this is the probability that you are looking for. That probability is outcome either over here. So this is the length of this interval times the value of this. What is the probability of phi 1, 1? Let's say 60 degree. Okay? So you have a value for that. And this is approximate because you are assuming that this is constant over this interval. So constant value, actually I should integrate it from here to there, isn't it? For phi. But I'm not integrating it. This is the reason that it's approximate. This value is the middle value times the length is the integration's approximation. So if I divide by dx, can I write this like this? dx dy. dy. That is it. So if I divide by it, I get this. So this is actually the following. At the end, you have derivatives. So this becomes the derivative. Okay? This becomes the derivative of this mapping function at this, let's say, operating point. If I have an operating point over here, operating point over there, essentially I'm approximating it by a straight line at this point. Okay? So after that straight line approximation, the only thing that I need is the slope over there. So that is the explanation of this. Again, this is one function of one random variable mapping. Please check your notes, earlier notes. This should be available. So the typical example in courses that we use in teaching this is the following function. Y is equal to x squared. Okay? With this function, x is the random variable. The question is to find the density of y. So with this example, typically we study this. Okay. Let me again erase this. Now, this is to refresh our memory. Let's say that we know what to do, or we know how to write this, and let's evaluate this formula. So what can I do? So the next step is, let's think about. So I should calculate the derivatives at some points, and then write the result. So how about this? This is, as I have said, uniform distribution, isn't it? This is uniform in 0 to 2 pi. Of course, this is the same. So if I write this over here, now what do I have? Uniform distribution on the numerator, 1 over 2 pi. Uniform distribution is taking the value of 1 over 2 pi, provided that, there is an operating point over here. Okay. Divided by, now derivative of this function, you take the derivative of this function, a times sine phi, but let me write 1, 1 because of this, and there is because cosine has minus sign, I have this. Why do we have absolute values? Because as we have said, even though this slope is negative over here, I need this interval's length. This is the reason that I take the magnitude of this. Okay. So this is the first one. So for the second one, second operating point, so there can be an outcome in this interval. Also, if I have an outcome in this red interval, which is the second operating point, the central is phi 1, 2. So that is, this is constant, uniform 0, 2 pi. So this value is 1 over 2 pi. Again, this slope, minus a sine phi 1, 2. Now the question is, I don't have phi 1, 1, phi 1, 2 on the left-hand side. I should write everything in terms of x1, isn't it? So somehow I should get this, phi 1, 1, phi 1, 2. So what are these phi 1, 1, phi 1, 2? So these are these points. So that point is phi 1, 1, x1. So x1 can occur, this is the center point. x1 can occur phi 1 to x2. So we have then the following issue. Given an x1, a times cosine phi is my equation. X1 is given, so I'm looking for phi's. X1 is given, I am looking for these phi values. So clearly, as I have said, we have two of them because of this cosine. So what are these? Phi is equal to plus minus cosine inverse x1 over a. Am I right? So if this is a over 2, this is 60 degrees and minus 60 degrees. That is it. So I got my phi 1, is one of them, plus cosine inverse. This, then phi 1, 2 is negative of them, cosine inverse x1 over a. Okay. So I got phi's. Now using these phi's, can I evaluate the sine function? I should be able to evaluate the sine function somehow. But how about this observation? Sine phi 1 is equal to 1 minus cosine square phi 1. Okay. So I already know their cosines. So maybe that would be easier. So do you remember sine expansion or cosine square plus sine square is equal to 1? So I'm using that. So if I do that, I have 1 over 2 pi divided by, so I have a, and I have square root of 1 minus, cosine. So these cosines are, cosine of phi is x1 over a. So I can put here absolute if I wish, because this is always positive. So this is, if you take the absolute value, a is always positive, a is amplitude, times magnitude of this, it is this, plus the second one, 1 over 2 pi. Now a, positive, the magnitude of sine phi. So again, I get plus minus issues, but they are also x1 square over a square. Okay. I have this. Because of this absolute, I have that. So what do I have? So at the end, I get the following. If I write this, this is my final result. F of xt1, which I call my first evaluation time, t1. So the density at that evaluation, so this is the variable for the density. Now I get this, 1 over 2 pi, okay, or 1 over pi because I have two of them, times a square minus x1 square. Let's move this a square inside of the square root, a square x1 square, 1 over 2 pi. I have two of them, so 1 over pi. So this is only valid if x1 is in between a and minus a, because otherwise I don't have, as you see, two solutions. So if x1 is, for example, over here, there is no solution. Okay? So if x1 is over there, meaning that, for example, this minus 2a. So clearly, there is no phi giving me minus 2a. So then this is 0, otherwise. Okay? So please remember, we have started with this sketch by saying something like this. That is it. Now, this is our density function, first order density function. Let me check if everything is okay. Okay, so let me sketch this density function. Well, I won't be doing a detailed sketch. So, just to see. So this is a function like this. So this is our f of x1, x1, x1. I have a minus a. When x1 is equal to 0, I have 1 over pi a. So this value is 1 over pi a. Okay. And so on. So let's see whether this makes sense. So we see that the lowest probabilities are around when x1 is small, x1 is like around 0. Okay? The magnitude of x1 is around 0 means I get low probabilities. If I'm closer to a, or closer to minus a, I have much higher probabilities. So how is it possible? Well, the reason is these slopes. So you see that when x1 is small, let's say it's 0, so the fastest or the steepest slope is around of this curve is at 0. So if you draw this, for example, slopes, let's look at the slope. So this is slope over here. Now this is slope over there. So the steepest slope is around to 0 crossing. Okay? Steepest slope is around to 0 crossing. So this is, for a fixed interval over here, gives you the shortest interval over there. Okay? Because the slope is very steep. Okay? That is it. So if this is very steep slope, as you see, I have 0.1 unit over here. If this is a very large interval like that, 0.1, let me see, 0.1 units over here will be mapped over here, and this will be mapped over there. It will be a large interval. If I make it steeper and steeper, as you see, this interval is getting, red interval is getting shorter and shorter. That is the idea. Okay. So this is the mapping that we have. So is this the end of this problem? Well, this is the end of first order p.d.f. description. Okay. Now let's focus on the second order p.d.f. So actually, as you see, this is the reason that we had an extensive review of random variables at the beginning of the course. So this is not something, you can remember without any refreshment in 2 years and so on. But this is a very important fact for our course. One function of one random variable mapping. Now let's see second order p.d.f. description. So what is the problem? Do we understand the problem? Now I have two evaluation times. Let me have the other one with black. So this is at t is equal to t2. Now at t2, you observe maybe this realization, or that realization, etc. So the density of t2 is also, at t2, is also like this, because it doesn't depend on time. Okay? You see there is no time dependence. There is no t over here. So I'm evaluating at t1, but you don't see any t's over here. In the random slope example, like please remember we have t1 times t2 divided by 3. So evaluation time was affecting the results. But this time evaluation time is not affecting. Now, the issue is not the marginal distribution, but their joint distribution. So how can I calculate the joint distribution? Okay, so how can I calculate, given that at the beginning of the problem, this is uniform 0 to pi, how can I calculate not one, but their joint distribution? Again, we will use this conditioning idea. Do you remember? For the random slope, we have done it. And we are doing it again for this example. Random phase cosine example. Let's see. Unfortunately, there is quite a lot of notation, isn't it? What do I mean by quite a lot of notation? Capital letters, small letters, conditioning, etc. and etc. But all of those symbols are important because, they tell us something. This is our communication, let's say, standard or language. Now, this is the joint density. We have found this. This is found. We are happy with this. Okay. But I have no idea about this right now. If I can find this one, this is the end of this calculation. Now, previously, this was easy for the random slope. Maybe you can remember in the random slope, we had something like this, a times t2, given that x1, a times t1 is equal to, this is an observation. So this is the thing that I'm telling you about notation. This is random variable, but I know that a times this is the random quantity. Since this is my observation conditioning, this is equal to x1, small x1, a value. So given that, what is the density of this? We have studied this. What is the density of this, x2 random variable? And we have found this very easily. Essentially, we did the following. We said a times t1, t2 over t1. But a times t1 is already conditioned to be x1, a fixed quantity. And that was the end of that calculation, okay, for that one. So can I do the same thing for this one? Let's give it a try. So f of xt2, xt1, x2 given x1 is the question mark. So what can I do about this? x2 is a cosine omega t plus theta, and given I know, let's do not write this one then, I don't have enough space, a cosine omega t plus theta, erasing this, is equal to x1. Let me box this so I don't erase it in case we need. But I don't think we will be needing this. That's over. Okay. A times cosine omega t is equal to this. So my first observation as an example, yes?
You forgot T1 and
T1 and T2, definitely. T1, so this is T2. This is T1, definitely. Thank you so much. Now, for example, your first observation is A over 2. So what can you say about theta? Then you say that theta is 60 degrees or minus 60 degrees. Am I right? If this is A over 2, well, T1 is equal to 0, let's say, okay? If this is equal to 0, T1 is, let's assume that T1 is equal to 0 for now, for the sake of simplicity. So if this is equal to 0, then I have two possibilities for theta, okay? So if I know this theta possibilities after this observation, then actually I know x2. Do you see the idea? Because if this theta is either 60 degrees or minus 60 degrees somehow from this observation, then x2 is, this one is either 60 or minus 60. Okay, that is the idea. Because the main issue is, now this x random process is totally fixed by this theta. So if I can update my information of theta from uniform distribution in 0 to 2 pi with this observation, then of course I can write the other samples. That is the idea. So what can I do? How can I do this systematically? Essentially, I need an update on theta and then evaluate this. From updated theta, I need to evaluate the distribution of x2. So we can work out that way, but let's also do the following. x2, a cosine, omega t1, or let me write it like this. Would you agree with this? x2, this part. Well, I didn't do anything other than adding and subtracting by omega t1. Okay. So why am I doing this? I will call this, my, let's say, alpha. Oh no, not this one. This one as alpha. This one as beta. Let's do a cosine expansion. Okay. So this is a times cosine omega t1 plus theta. Cosine omega, let me write delta t because I'll be writing the same thing again and again. So let me introduce this delta t. Okay, let me introduce it over here. So cosine alpha, cosine beta minus a times sine of this sine omega 1 plus theta and sine omega delta theta. So this is the cosine expansion. This is the reason that I have this. So this box is alpha, this box is beta, again alpha, this is beta. So cosine alpha plus beta is cos cos minus sine sine. Okay, that is it. So why am I doing this? Well, now I can express this thing as summation of two terms. And I also know that this is equal to x1. Actually, this is then equal to x1. Am I right? A times cosine omega 1. This is, so this is known times cosine omega delta t. Okay? Minus, but I have the cosine as x1, but I need the sine of this. So how can I have this? Well, how about this one? Let me give it a try. If I insert x1 from here, I have a square. Okay. Take it out of the square root, I have a. And 1 minus cosine square, I have this, which is good. Okay. But the issue is, again, they are coming in pairs, plus minus pairs, isn't it? Because of the square root operation, essentially. So this plus minus will be affecting. So I have, let's say, minus plus, like that. I have two possibilities. So this is either this or that, with plus minus sign. Sine omega delta t. Do you agree? So this part is this part. I know this is this. This is x1. So what do we have? From x1 information, I can identify this thing and this thing, but there is some ambiguity still with this one, and so on. So what do we see? So we observe that, indeed, after we, let's say, obtain observation, let's say x of t1 is equal to x1, we have indeed two possibilities for x t2. Okay? So this is, remember, second random variable, x t2. So which one is one of the possibilities with the plus sign over here, the other one is with the negative sign over there, and that is it. So let me write them as x1, what was this? x2 possibility, number one is, well, okay, x1 cosine omega t with plus sign, a square minus x1 square, and I have sine omega t. The second possibility is with negative sign, x1 square sine omega delta t. So let's keep this. So these are the two possibilities. This is strictly due to the property of the cosine. Okay. So this was easier for the random slope example because it was just, simple scaling. This is a little bit complicated for the cosines because cosine expansion is a little bit more complicated. So I have cos, cos, sine, sine. It's essentially related with that. So now the issue is, okay, so I know that indeed there are two possibilities as we have discussed at the beginning. If I have a over 2 as this, we have said that this theta is like 60 degrees. So it gives us two possibilities, 60 and minus 60. Okay, so we see the same facts. Okay. Now, then x2, which is x evaluated at t2, given x1, then has the distribution of I have this. So what is this? This is the conditional density that we are looking for, but I will explain this a little bit. So this is the conditional density that we are looking for at the beginning of this problem, this part. So why do we have 1 over 2's? Well, if I make this observation, x1 is equal to a over 2, then as we have said many times, two possibilities, 60 minus 60, and those possibilities are because of the uniform distribution. We should actually prove this, but let's do not prove it anymore. They are equally likely. Okay? We cannot say that this is more likely to be 60 degrees or less likely to be, I don't know, 100 and 300 degrees and so on, because of the uniform distribution. Actually, the only thing that you need to do is, if you can update your theta information. At the beginning you have this information about theta. After observing x1, let's say a over 2, you get the posterior distribution for theta. So given that posterior distribution, then this will be again, x2 will be a mapping of this density to x2. Okay? That will be something like that. So that explains this 1 over 2's. Because of the uniform distribution, I have that. Now, final result. So let me write it over here. So let's keep this. So the final result is, I have the following. We're almost done. This is this density. Other. So this is our marginal density over here, times, now I have 1 over 2 times delta x2 minus x21 plus 1 over 2 times delta x2 minus x22. Okay, so this is our joint density for two observations. Okay. So this is a function of x1 and x2 as expected. x1 appears over here. This is piecewise defined. So first function, piecewise defined function, times second function. x1 appears over here, x2 appears over here. How about this? This is a function of both x1 and x2, as you see. You know, I have x1s over here and t1, t2s over there, and so on. So this is just function of, you know, x1 actually. This is a function of x1, as you see over there. Okay, that's all for today. We will continue with more definitions. By the way, please look at the homework. Homework problem is simpler than this. But if you study these two problems, random slope and random phase cosine examples, you should be able to solve the homework problem very well. Okay? Please think about these. These topics are not very easy. One function of one random variable mapping, this kind of calculations. I recommend you to go over these calculations one more time on your own and then attempt the problem. Homework problem. Okay, see you later at the next lecture.